Okay, for those of us who are just joining this recording, you have missed nothing seriously. We are going to be doing two things today. We're going to go through the practice exam that was just posted on CCLE. And then after that, I made some additional slides, practice problems, reference materials that we're going to just kind of walk through as well. So without further ado, let's do this. So let me pull up the chat as well, just make sure I'm not missing anything here. Okay, cool. All right. So question number one is an interpretation of coefficients in a linear regression. So I'll give you guys a moment to read this problem. And then I'll kind of talk through it. I won't necessarily, you guys can read the screen clearly, correct? Or you can sort of, if you have it pulled up on your own, you can read it, right? Well, let me frame that another way. Can anybody not see or read the question currently? Okay, I will take that as a yes. So yes, I'll give you guys a second to read this, but in essence, at a high level, this type of question is really talking about sort of problem formulation. It's about thinking about sort of modeling a relationship between your desired label, your desired sort of thing you're trying to predict, and the features that you're given. So, you know, we talked about that from a part of the job of a data engineering thing is thinking about that relationship between your labels and your features, and you know how you might frame or structure the model is that you create. And so really that's what we're looking to do here. For something like this, there isn't for a question like this, if you get asked this, there isn't necessarily a right or a wrong answer to this. I mean, there are obviously right and wrong things that you can do as part of the answer, but there isn't necessarily one ultimately correct answer to this approach. Having said that, you know, we are going to look at kind of a few things. So the first thing we note is that we're trying to model a continuous variable here, the amount of growth, that is y. So that immediately tells you we're looking at some kind of regressionary analysis. This isn't a classification exercise. This is a regression. And then we're told that we have sunlight here, which appears to be just sort of a general numeric variable of the amount of sunlight you're given. And then plant type X2. And we're told that there are 3 different types of plants. So we know that this X2 is categorical and it contains 3 discrete values. So that's the problem space that we're given. In terms of kind of thinking about how you might approach this and maybe what you might sort of want to do in this. So, so the first, I guess there are a few things to know. So the first thing we would say is you'd probably want to structure this as a linear regression. You'd probably want to do it in terms of both sunlight and X2. Since this is a categorical, we may also want to one-hot encode it. A decision that you will want to make, and there's not, again, a right or a wrong answer, but you should be explicit about this, is since there's 3 discrete options, do you one-hot encode all 3? Or do you just one-hot encode, let's say X1 and X2, and then allow sort of the third plant to sort of fall into the y-intercept, your B0, if you will. So that would be a choice for you to make and then for you to kind of discuss. And again, there isn't necessarily a wrong or a right answer for that. And we've kind of discussed that, I think, a bit more in discussion as to why you'd want to do that or not. But both are technically correct, and both of those you would be capturing explicitly that third plant option. But again, it's just something to sort of think about when you're structuring this model. The final thing that we may want to do is, because we're looking at the relationship specifically between sunlight and plant type as well, we may want to actually model this as an interaction term as well. So thinking about if you can think about sunlight as maybe something that you can discretize, if it's not necessarily a continuously valued variable, but actually has, you can either block it or, turn it into sort of some form of categorical, there may be some kind of cross, what's the word for it? A cross term. You may want to do a cross term between, your X1 sunlight variable and your X2 plant type variable as well. So again, none of those are necessarily right or wrong, but those would just be factors that when you're writing out your solution, you may want to speak to for this problem. So any questions on 1A specifically?
Yeah, quick question.
Mhm.
So, for the professor, would he be pretty flexible in our responses? Because if we want to hot encode, like we could have like data one, data two, data three, data four,
Yeah.
um, like more coefficients than maybe like expected. So is that like all right?
Yeah. So again, for precisely when you're dealing with an open-ended question like this, there are right or wrong answers. So like this is probably not going to be a classification problem unless you can, unless you can make the argument for it to be classification. You're looking at building a regression model. Um, you know, you may, unless you do something crazy like saying I'm just going to ignore sunlight as a variable and just focus on plant type, like that's obviously wrong. But beyond that, there, as you can see, there's a lot of flexibility in your approach. And really what we kind of want to see for this problem is you kind of go through the exercise of talking about sort of building that relationship between your label and your features, and then thinking about the relationship within each feature, how you represent it, whether or not you sort of keep it static, whether or not you do some kind of transformation to it, like a one-hot encoding, and then finally, whether or not there's kind of any relationship between features, such that like a cross term between them would be warranted. And so generally, I'd say those are kind of when you're thinking about a problem like that, those would be kind of the three things to explicitly discuss as part of it. But again, we're not giving you specific guidance on that. So I don't think, as long as it's kind of as long as it's sort of a sensible thing, I think you'd be fine. But yeah, great question. Okay, so actually in the chat, will there be a solutions guide posted? It's a bit unclear on how to write. I don't think I can ask Midget if we can post a solutions to this, but I don't believe we're doing that. I think he just wants us to post the practice exam. But again, just generally, this would be sort of, you'd write this out. If you're asked a question like this on the exam, you would just kind of write out the type of model you want to do, the relationship between the model and the label and the features, how you would handle each of the features, and like we said, whether or not you want to do any kind of cross term or transformation. And then you may want to be explicit about sort of how features are represented individually. So I think that would be, that might be just kind of the things to do for that. So, okay, good. Oh, okay. So how do you interpret the coefficients for your model? So that we sort of asked something similar in the homeworks before, but you would essentially say, okay, so, for X1, there's a beta 1, and that's the impact that light has on growth. For X2, there's a beta 2. So that's the particular, that's the impact that particular plant type has on whatever. And then if you have like a cross term or one hot encoding, you'll have sort of additional features and additional coefficients. And so you may just want to sort of elaborate on what each of those coefficients represent. But yeah, so thank you for calling that out, Wei Yuan, because you in this case, you would just want to be explicit about that. So, okay, so yeah, so unfortunately, so Chelsea had a question about whether or not we can type our answers. I don't have any guidance from Professor about the specific logistics about the exam itself. When it was proctored last quarter, we had everyone write out their answers and then just kind of submit the written answers onto Gradescope, but I don't know what Majid's rules will be. I think on Tuesday he'll clarify exactly what he'll expect for that. So yeah, I'm sorry I can't give you sort of a better answer for that. So then let's see. Okay, so then there's yeah, just stop me if you have any questions on this. But so okay, for part B, so then how do you test the null hypothesis for each independent variable x1, x2 to indicate if they have a significant correlation for the dependent variable y? So here, so we talked about last week in discussion as part of like project 3, doing a statistical analysis where, you know, and sort of calling up those things. So we can sort of run the regression analysis based on that. We can look at the mean and the standard error terms and use that. That'll generate our p-values, they'll generate our t-scores, and that can indicate whether or not those particular features are significant or not for that variable. So, you know, essentially all you would just write out there is that you would run a standard statistical analysis based on your regression. You'd look at the p-value for significance. You'd look at your t-score to see if it crossed the critical threshold. So that's really all we would look to write out for that one. Okay, that is problem 1. Okay, so problem 2. So this is one of these problems that at first glance is like, what the heck? And then, but we dig into it and actually, hopefully you'll feel like you're pretty well equipped to handle it. So they say, okay, I'll give you a chance to read this, but essentially there are a series of graphs here of classifications with decision boundaries. So we see these things here, and we have to match a problem. We have to match a different sort of learning model to, sorry that my screen is kind of acting weird. So here we have 8 different sort of decision boundaries that learning models have generated, and we have to try and sort of match our a set of these things here. So a linear SVM, a kernelized SVM, perceptrons, logistic regression, decision tree, random forest, a neural net with a ReLU activation function, and a neural net with a tanh function. So if at first glance you look at this, you might be saying, nothing that I have learned in lecture has prepared me to look at a random decision boundary and automatically tell me what learning model it is, right? But once the immediate panic subsides and we kind of start mulling this over and think this through, we'll actually find that we can kind of think through the logic of each of these learning models and come up with a reasonable expectation and explanation for which model is which. So let's start with sort of the obvious ones here. So we can see that we're within our, so we have sort of these curved ones, we have this crazy one, we have these sort of, I guess, squared off ones, and then we have these 3 linear ones. So let's start with the linear ones because those are probably the easiest ones here. So of our linear model, so here's our options here. Which of these do you think will produce generally speaking, will produce a linear decision boundary? Okay, good. So Dean and Akshay in the chat. So linear SVM, yes, perfect. So those are going to be linear decision boundaries. Okay, so we've got one of them. We know one of those 3 is going to be a linear SVM. What else produces a linear decision boundary?
Perceptron.
Good. Was that Tommy? Yes. So Perceptron. Yes. Yep. And Isabel in the chat, Neil in the chat. Yes. Okay. Perceptron as well. Yes. So if you remember, Perceptron is just a quadratic equation as well. So that's going to be a linear decision boundary. So what's going to be our third one? Okay. Akshay. Perfect. Yes. Logistic regression. So remember, even though logistic regression has that funky like sigmoid transformation, everything, that the end decision boundary is still a linear decision boundary. It's still that quadratic form. It just happens to then equal to that the log of the odds ratio and everything like that, but it itself is still a linear decision boundary. So now we have 3. So now we have our 3 candidates right there. So let's see if we can try to kind of knock those 3 off. So A, B, and C. So let's kind of look at the relative differences between them. So we see that C, the decision boundary is equidistant between our 2 classes. Whereas in A, it's slightly skewed away from the majority class and towards the minority class. And then for B, we kind of see that it just sort of is, it's a linear decision boundary, but it's kind of haphazard. So does that give you guys any thoughts on what might be what? Okay, and Tommy, I'll get to your question about decision trees in a second. Okay, so the equidistant, okay, so Rohit, the equidistant one is SVM. So good. So that's a good thing. So if you recall in SVM, so if you remember, we want to develop that hyperplane, and we do that by looking at the support vectors, the one that are nearest to the sort of the divider, and then choose one that maximizes the margin between them. So indeed, the one that's equidistant between those two classes would be the SVM. Good. So, okay, so C is going to be our linear SVM. So now one of these is going to be a logistic, one of these is going to be perceptron. What do you guys think? What might be a factor driving one versus the other?
Well, Perceptron just keeps turning the hyperplane until it just successfully classifies all of them correctly. So I guess that doesn't really help though, actually.
It does. It does. And I'll tell you, let's extend that logic a little bit further, because we said, so remember, you're exactly right, Akshay. We said that a perceptron would keep running until it achieves a clean division between the classes, right? But the key thing is there's no underlying loss function. There's no gradient model there. There's no inherent optimization of that separation, right? It will run until it literally achieves any kind of clean separation, but it does nothing beyond that. Whereas something like a logistic regression, it does have that underlying loss optimization function that tries to minimize the overall loss. And if you think about it, if you're trying to minimize your overall loss, you can see why the resulting decision boundary might sort of influence away from the majority class to the minority class, kind of build sort of an added buffer here to say, let's be extra careful when we're classifying all of these X's. And so let's sort of build in a little bit of that buffer. Whereas this thing, this is completely haphazard. It just happens to be arrayed randomly there. There clearly is no optimization. You know, something that falls right here, let's say, clearly should probably be a minority class, but it will likely get lumped in with the majority class. So yes, so you were exactly right. So that was kind of the key point is part of when we think about how these different models approach classification is there an optimization step, and how do they optimize? And so for SVM, the logic was it optimizes by creating the maximal margin between the two classes, support vectors. For logistic regression, it tries to maximize it by reducing the loss function, the error term. So you can see how it might sort of skew away from a majority class to minority. And again, Perceptron, there's no inherent optimization. So it might look like that. Okay, so 3 down, 5 to go. So let's kind of look at some of the other ones here and see what this might be telling us. So, so Tommy, let's kind of jump ahead and think about your thing. So you asked whether or not a decision tree was a linear classifier. So I guess the answer I would give to that is yes and no, because it has a linear decision boundary based on sort of the various axes, right? Because it's making those clean splits. And so just looking at that, you know, what would make sense for that? Well, G and H sort of immediately pop out to us on that. But we notice kind of important distinction here, whereas G is sort of nice, clean, linear decision boundaries along each axis. H is sort of this kind of a little bit, you know, not quite right. There's a little bit of exactly, it's an unstable line. So looking at that, and remember, if we go back to our options, so if we have two sort of tree-based things, we have a decision tree and a random forest. Well, you know, it sort of logic would dictate that the clean sort of basic thing would be the decision tree, because again, the decision boundary there is a straight line, whereas a random forest would be the average of decision trees aggregated across that. So if you're averaging across it, you might get these sort of minor fluctuations based on how the individual decision trees handle that. So, okay, so hopefully that that logic makes sense, but you sort of look and you're like, oh, well, that seems like a nice, clean decision tree boundary. And then when we're getting this kind of messy thing here, well, we know that an individual decision tree is linear, but if I'm, aggregating and summarizing and summarizing across decision trees, I might get little minute fluctuations, which would be a random forest approach. Okay, so now we are 5 down, 3 to go. So what we have left is a nonlinear kernelized SVM, and then we have 2 neural net functions. And so this one I'm just going to kind of throw out there and say, okay, well, this is this crazy decision boundary that looks nothing like any kind of clean linear separation. It's just kind of all over the place. Well, that's exactly when we were talking about kernel functions and how when you sort of dimensionality reduce your kernelized function down to that lower thing, it gets these weird kind of balkanized decision boundaries. I don't know if you guys remember that the graphic with the cats and the dogs, where we had that nice clean plane when we were in 3D, but then we went down to 2D and it just looked all like Swiss cheese. Well, that's kind of what we're seeing here. So, that might be linear on the sort of higher order kernelized dimensions, but in the dimension that we're visualizing, it clearly is not. So that's a little bit of a kind of a giveaway there. The final thing for us to figure out is we have these 2 things here that sort of look like neural nets. And then for that, really what it boils down to is the difference between the activation functions. So ReLU and TAN. And does anybody just kind of quickly remember what either of those outputs are? Okay, ReLU is good. ReLU is 0 when output is less than 0, and then it's just linear from there on out. And then TAN is TAN is more smooth. Exactly. So if we look at these here, so these kind of these sort of flattened areas here would seem to be indicative of areas where maybe your outputting is 0. The other areas where you're outputting sort of linear curves there. So that would suggest a ReLU thing, whereas this, where it's smoother, that would suggest a TAN activation function.
Wait, what'd you say indicates ReLU just now?
So the fact that you have these kind of this, rather than it sort of being a nice smooth function, you have these sort of areas where it's a bit flattened.
I see.
So because ReLU is sort of, it's piecewise linear, right? We have sort of components where it's linear and then component where it's not linear, right? That would seem to indicate a ReLU thing, which is, if you think about it, ReLU is piecewise linear.
I see. Thank you.
Yeah, so this is definitely one of those problems that, like, I have no idea if we're going to get asked something like this on the exam, but it's very, one of those things that, like, you see it and you're like, nothing in lecture has equipped me to deal with something like this. But it's a question, and we'll talk about this more in the slides, but just like in general, taking a step back and saying, even if I haven't seen this particular permutation or this particular sort of structured problem, what I know about the underlying learning model, and again, sort of like how it's structured, how it achieves division, how it sort of, whether or not it optimizes, things like that. Generally speaking, that should give you kind of enough of an intuition that looking at this, you should be able to say, okay, this is how to approach something like this. So yeah, any questions on this? All right, moving on. So, okay, so this is question 3 here. Move that to the corner. So for this, it's saying, okay, sketch out the approximate first principal component of the data. Let's see, we create as much as the data is center. Okay, so, and then the other thing that sort of they mention here is that's worth noting is that on B, C, and D, the clusters are equivalent in terms of distance. So again, this is something that you haven't necessarily sort of directly dealt with in lecture or in sort of the homeworks or problems, but hopefully this is something, if you have a bit of an intuition about sort of what PCA is and how it works, you should have a kind of a sense of how to do that. So at a high level, what is the first principal component? What is it that we're being asked to sketch here?
You would choose the dimension of greatest variation or variance. Yeah.
Okay, I confess, Tommy, I didn't quite catch that. But I'm seeing in the chat, so Neil, I think you had a really good, concise definition there. It's the direction of the data that explains most of the variance. So then let me, I think this is just easiest if I display it here. So, okay. So then let me just display. So essentially we're looking at kind of a linear representation of the sort of the axis that explains the majority of the variance that you're going to see. And so, you know, and generally speaking, you kind of want to look at min and max, but then again, you also want to look at the relative density of the graphs. And so this one's probably the most easy one to interpret here, right? Obviously, data is kind of clustered along this seeming axis here, where most of the variance is kind of falling along this thing. This is a little bit tricky, but if you kind of extend that logic, you can kind of think about it, because even though each of these individual clusters tend to vary along here, because we're looking at them in summation, you sort of aggregate them together, at which case now the magnitude of the variance really becomes along here, where you're seeing a shift really along here. Same idea here. Even though you have these nice individual clusters, because you're simply looking at that vector that explains maximal variance, you're going to have to kind of extrapolate that from there, and that would be something like this. And in a similar vein here, because all of this data is clustered here so heavily, that kind of brings down the variant, the line to here. So, and one thing that I should note that actually ties into our homework, because there's a question about data, what kind of data is well suited for PCA. And this kind of problem, I think, gives us a little bit of an intuition on like where PCA performs really well and where it doesn't. And so obviously in this first example, where the data is kind of very nicely and linearly arrayed, PCA works great. But you can begin to see how in these other instances, maybe PCA doesn't really have the same kind of explanatory power that that maybe we would ordinarily assume, right? Like, is this really a useful representation for variance when you have data clustered like this? Or, for instance, in this example, is this really useful? It's not as obvious that PCA performs as well when you don't have that nice kind of linear distribution of data. So again, one of those things that you haven't necessarily kind of explicitly talked through, but if you sort of internalize the concept of PCA as being sort of projecting your data onto the sort of vectors or axes that most explain the variance, and you sort of internalize it, then it's just then it's just looking at it and saying, okay, well, what if I draw a line through my data, sort of what line seems to explain most of the variance in the values that I'm seeing. So
I have a follow-up question.
Mhm.
Oh, so in graph B, why wouldn't the line go from the bottom left of the left blob to the top right of the right blob?
It's a good question. You're saying, like, why doesn't it skew like that?
Yes.
Good question. So I think the argument to be made for here is because of the density, because this clusters right around here, right? These are the most dense regions of the data. So I think it's not, and that's really the other thing. So you have to look at both the magnitude of it, but then you also have to look at the density of it. And so I think because the density is arrayed along here, So the shift is there, but the density is right along there. And I think that's why it's sort of angled a little bit upwards and through the center of those clusters.
Okay, that makes sense.
So I think the density is something else to consider when you're thinking about PCA, because it's the total variance across your entire data set. Okay. So that is problem 3. And let me just pull up the chat here. Okay. So bias, variance, and regularization. Okay, I'll give you guys a second to read this. Okay, yeah, okay, so let me, sorry, so I need to scroll for that. Okay, so then just really quickly before I scroll over, so this is asking, so you're going to see 3 figures, you're going to see 3 decision boundaries that are a result of 3 different classifiers, one of which is overly biased, one of which has sort of too high a variance, and one of which is a relatively good fit. And then they ask you to kind of sketch out a graph where you demonstrate how training and test error for each classifier will change over time during the course of training the model. So let's see. And then explain how you expect each classifier to perform on the test set. And so this is sort of a qualitative concept here. And let me see if there is a, okay, so here is our 3 classifiers. We have A, we have B, and we have C. So again, this is a conceptual question, and what it requires is that you kind of think through the problems of bias and variance and how that might impact both the resulting sort of contour of your decision model, as well as sort of thinking through, if you were sort of modeling the performance of those variables, what that would look like. So let me throw this to you all here, and what is, if we have a model that's too biased, what does that mean? Okay, high error. Okay, so let's clarify here. Both, if there's too high variance and there's too high bias, the error is going to be high in both of them. That's going to be true. But I guess the question is, what will those errors, why will those errors occur? Okay, so you know what? I am going to jump ahead here. I want to actually, let me stop sharing. I want to pull up, because I actually have some slides on this, and I feel like it would be good for us just to kind of jump ahead to that. Because I think this is kind of a nice just concept for us to work through. And if I'm just looking at the chat, it seems like we're not fully on board with what's what on that. So, okay, so let me just jump ahead here to this, and we can kind of just talk through this. So bias at a very high level is the idea. Think about like a real world term for bias. Bias is when you take your own perceptions, your own sort of beliefs about something, and apply it to whatever that whatever that situation is, right? If you're biased about something, it means you're walking in and making assumptions that maybe aren't necessarily true. So if you think about that kind of that plain language sort of meaning about that, bias is also sort of analogous to the idea of underfitting. It's the idea that I'm not going to bother to learn a representation of my data. I'm not going to bother to model it accurately. I just have this idea for what the model should be, and I'm just going to apply that. And that's my bias. So that's sort of the first thing. Variance is, right, so if you think about the word variance, it's sort of about changes and dissonance and discord. Variance is the idea that your data, may be indicative of broader trends, but there's a lot of noise within that. There's a lot of sort of chaos. There's a lot of things that aren't necessarily statistically representative in your sampling. You may have outliers. You may have things that are sort of oversampled relative to the general thing. You may have things that are undersampled relative to the sort of overall population. So it's the idea that that your testing data set will vary from the universal model. And so your sweet spot when training your model is you want to get something that sort of properly kind of models the general contours, the general patterns of your data, but doesn't go overboard, but doesn't like try to get every particular instance, every particular outlier. It's not kind of molding the model to the point where it is so overfitted it looks like the topography of a countryside, right? So as many of you are saying in the chat, overfitting is an example of variance. When you are overfitting, you are capturing all of that noise and you are injecting it into your model. And so when we think about sort of what our goal is when we're trying to train our models, it's finding the balance between those two. It's recognizing that, there is we do need to train our model. We need to learn something about the data in order to get it. But at the same time, we can go too far with that. There's kind of a point where if we keep going beyond it, at that point, we're no longer learning general trends. We're now learning that specific variance. And as a result, we sort of begin introducing errors that weren't there in the past. So you can kind of see this here. So this graph, I think, is a really nice representation of it. So the blue term here being the overall bias in your model, the red term here being the overall variance in your model, and the total error being sort of the yellow term here. And this is, and you can think about this as the amount of prediction error. So this is the amount of error in your testing data. And this is model complexity. So the longer you train your model, what happens? And so the first kind of thing here is bias. So when you start out, your bias is very high, right? You haven't really done any training. You haven't really learned anything about your model. You've just made your initializing assumptions about it. So understandably, your bias is going to be very high. Conversely, your variance is going to be very low, right? You have learned nothing about your model, so there's no variance because you haven't bothered to learn anything. Then as you begin sort of training your data, very quickly your bias is going to fall off. You're going to start to learn some features, you're going to start to model it, you're going to start to do that, and your bias is going to go down. Conversely, though, your variance is going to start to go up, right? As the more and more you train your data, it's going to go up over time. And then as you can see here from this map, there's kind of that sweet spot here where your total error will sort of begin to diminish at time too, right? When you start out, your bias is very high. So the amount of error you're going to get from your bias is very high. So we're getting a ton of error here. As our model trains, bias goes down, total error goes down, variance starts going up, but not really enough yet to impact performance. And then we hit that sweet spot there where, again, our bias is sufficiently low, but we haven't yet overfit our model. But then, what happens when we keep going? Well, obviously our bias continues to fall, but now we start seeing we're hitting a problem with variance, where now we're beginning to overfit. And so as we're doing that, we're introducing new errors that weren't in our model previously from overfitting. And so our error tends to go up. So conceptually, again, our job and our goal at a very high level as data scientists is to really kind of end up here. This is the sweet spot for us. So, and everything we're doing about like loss functions on the one hand to try and minimize bias, but then doing things like regularization to try and kind of minimize variance and things like that, right? That's kind of all playing off that trade-off between them. So hopefully, I think that's kind of a really useful sort of taking a step back, because we always talk about all these things like loss functions and, when the models converge and, test data versus training data and regularization. Hopefully this kind of puts it a bit into context as to the broad picture for why we're doing what we're doing. But let me pause there. Does that sort of conceptually make sense?
Is the error the test error?
Yes. So specifically it says prediction error. So that's the test error. Because training error, if we were graphing training error, it would continue to fall. It would just fall much like bias does. Because remember, if you overfit, you're essentially perfecting the model against the training data. So eventually, your training error would go to 0 because you would overfit to it. So you would perfectly sort of model every particular nuance or sort of variant in your data set, but that's obviously not what you want. So yeah, so this is prediction error. This is your testing error, not your training error. Good question.
Just to make sure I'm understanding like bias correctly, the idea is like our model's not complex enough, so we like learn a couple features and then we're like, oh, this is how everything behaves, whereas that's not really correct. Is
Yeah,
that the idea?
yeah, that's exactly a way to think about it. Again, just, start from just the plain text meaning of bias, where I take my preconceptions of an idea and I apply it to something I'm uninformed about. So it's the exact idea. You haven't informed yourself about the data enough. You come up with whatever your predispositions are. So yeah, you either haven't trained at all or you've insufficiently trained against the data to learn adequately about it. Yeah. So, okay, so with that in mind, let's go back here. So now that we have that idea in mind, which of these models do you think has overly high variance? Which one do you think has overly high bias? And which one do you think is that, sweet spot where we've kind of balanced it perfectly? Okay, what do you guys think? Okay, C has high variance. Perfect, right? We're getting this. It looks like it looks like a map of a coast, right? Where you have your little peninsulas and inlets. Yes, so exactly right. So where we get this sort of Swiss cheese type approach, this is very clearly overly high variance. This is overfit to heck. A is high bias. Exactly right, John. So here we just have casually driven the line. We're like, this is our decision boundary. And we're like, well, what about all of what's going on here and what's going on here? And you're kind of missing all that. And it's, well, I'm just that. But yeah, B is where we want to be. I'm sure that was deliberate. Thank you. B is where we want to be. So exactly right. Okay. So then the next question is saying, can we plot, explain how you expect each classifier to perform on the test set? So, and remember, you see, draw okay, so what's it asking? Draw an approximate graph where you demonstrate how the training and test error for each classifier will change over time during the course of training the model. So hopefully we have kind of a good concept for that, but let's take a look at this. So B is where we want to be. That was the good one, right? So that was where where our model. So this is sort of error, and this is our training thing. So if you recall here, this is sort of the good one. That's where we want to be. Here we have kind of nicely trained it, but we haven't necessarily overfit it. And as a result, our testing error is, now one thing I'll note here is that it's almost always the case. Not always, right? You will get these weird performances where your test data will be better than your training data, but almost always, because you train on your training data, that will almost always produce less error. So it's almost always the case that your test data will be a little bit worse than whatever your training results are going to be. But again, this is good. This is nice, right? This is clearly not necessarily overfitting, and we're seeing a nice sort of decrease in our testing error as time goes on. C is our overfitting thing. So here, remember the key thing we said here is that our training error when we overfit is going to continue to fall. It's going to continue, right? Because as we get better and better, we're going to kind of create this thing here. We're capturing every particular instance, every particular sort of exemption here. We're capturing. So eventually, if we really overfitted, our training error goes effectively to 0. The problem is the impact in our overall performance in our test thing levels out. And if anything, it probably gets worse over time. I think this should actually slope back upwards a little bit. I think this is a little bit wrong, because the more you overfit, the more you actually introduce error over time. So you would see this model go down, but then again, as you overfit it, you would sort of create this. Now for this one here, the bias, we effectively sort of, this is kind of the lazy learning model. Because remember, if you're looking at this as being epochs, clearly we maybe do a little training, but very quickly we just kind of stop and we don't really do anything more to it. And so, and you kind of see that here, like, okay, well, we start out high and then maybe we did a little bit, like Axel said, maybe we trained it on a few of our features, maybe we ran a few epochs, like we did something with it. We got some improvement in performance, and then we just kind of said, all right, good enough. And the sort of the key thing here to note is because we haven't really bothered to learn the model of our data, it's pretty much going to be expected that its performance would be pretty uniform between test and training data, because it really hasn't leveraged anything in the training data to improve itself. So, all right, any questions on sort of what those graphs are telling us? So again, I have to say, and again, unfortunately, I don't know, because Majid didn't teach this course last quarter. It was a different professor. So I don't know to what extent he's going to replicate these precise questions. But I think the hardest part that people had last quarter when they took this, it was less about the actual information. And it was just that they had never been asked to conceptualize the material in the course in that particular way. And I think that was what made this exam harder. Maybe than it sort of ought to be, right? Because, so I mean, he said this was the test to use, so presumably he's going to try to kind of, I guess, replicate these type of questions. But in general, if you get asked something like this on an exam, the thing that I would sort of emphasize here is that, like, don't necessarily immediately panic if you look at this and say, like, I've never seen something like this before, I don't know how to conceptualize it, and just kind of take a step back and say, like, okay, here's the information I have, I can work through it, and I can sort of understand and work through how that would look, because I have the information necessary to solve this. Okay, I'm seeing a request for a 5-minute break. So yeah, so how about we finish going through the exam, then we'll break, and then we'll do the slides. How does that sound? Okay, I'm going to take that as a roaring and resounding yes. All right, question 5. We're almost done. We're almost done here. Okay, so question 5 is, okay, so perceptrons. So you're given details about a perceptron here, and we're going to do another practice. I created in my slides, I also have a perceptron question. So we're gonna get pretty well practiced on perceptrons here. But perceptron, as you know, is that one neural net. In this case, it takes 2 inputs. So you have an X1 and X2, and then it's a binary classifier. So it just outputs a 1 or a 0. And then we get sort of the weights. So all the weights for this are initially equal to 1. And then the learning rate, which is again our multiplier for that, is equal to 2. So that's the conditions we're given for this. Where's the next page? No, okay. So, and then it says, okay, given the following set of data, show how the model would update after each point. So essentially, this is kind of learning to update the model. And then you may only need to solve 1 complete epoch on this. So let me actually go back to my slides if you're okay with this. Where's my perceptron? Okay, because I feel like it might just be good at this point for me to just walk through this example. So if you remember from what we covered previously, for perceptron, we have the sort of the weighted sum of my inputs. So I multiply each of my features by the associated weight. I also have a bias term here potentially. I then sum it all together, and then based on that, there's a sort of an associated step function. So in this case, if it's greater, if whatever the final value is greater than 0, I output a 1, and 0 otherwise. And if you remember here, we had our learning function here, which is sort of how we change the weights, the delta of our weights here. And so this is our learning rate here, C. So in our test example, that's 2. This is our actual value, our y actual. This is our predicted value, our y predicted. And then this is just the magnitude of the feature. So remember how we said it was important that we sort of adjust for the relative scale of our features. By sort of multiplying that, we ideally kind of correct for differences in magnitude. So remember, this term here was really, really important for kind of helping us shift the direction, because if the actual prediction is 1 and we predict 0, then clearly we're not crossing this threshold here, right? Clearly we need to have something that was greater than 0 and we didn't get it. So we need to, our delta has to be positive. We have to increase our weights to get it to be positive. Conversely, if this is a 0 and this is a 1, then we've predicted something where we shouldn't have. So clearly we have output something greater than 0. We should have output something 0 or less than. So clearly we need our weights to go down, so our delta is going to be negative. So that's just kind of the mechanism for how our perceptron learns. And then, so here's one thing I'll say that'll just kind of make it easier for you. And so here I have an example of this. We have 3 neurons, and we have the actual value here. And then we have a bias term. So in this case, the bias term is, I think it's just 1. Yeah, it's 1. And so the way I would recommend doing this is just writing this out as a table, the way I sort of have it here. So we have, where are my, oh, okay. So how you interpret this. So we say we start out, all the weights for these, including the bias term, are 1. And then we have these 3 data points here. So we have x1 equal to -8, x2 equal to 3, x3 equal to 4. And so then, and then we just plug that in. So in this case, because everything is 1, we just sum the numbers as is. This sums to 0. So if you remember, our rule is anything greater than 0, we assign a 1, 0, you assign 0 or less, you assign a 0. So we sum to 0, we predict to 0, our actual one is 1. So because we made that error, we're going to have to correct. And because we undercorrected, so clearly we're going to have to, clearly we're going to have to sort of correct it, and it's going to be generally a positive shift. However, not the resulting change won't always be positive, because remember, you're multiplying by that value. So sometimes the shift will adjust in a different way than you expect. But let's use this term here for this one. So our learning rate is, did I say, okay, learning rate is equal to 1. Okay, so I made this very simple. So our learning rate is going to be 1. Our t minus z here is 1 minus 0. So 1 times 1. So this is just 1. So times whatever the value of x is. So whatever this is, I'm going to multiply by, I'm going to multiply by whatever my x value is, and that's going to be what I'm going to adjust my delta by here. So in this case, I'm going to multiply by -8. That's resulting -8. If my initial weight was, for this one was 1, now it's going to be -7. For here, I'm going to have 1, my delta is going to be 3, my resulting weight is going to be 4. And here, again, 1, my delta is going to be 4, I'm going to be 5. Does that make sense how I'm calculating the shift in my W? Is that
actually, why are you adding for 1 plus 3 and 1
yeah,
plus
so remember, so this is your okay, so good question. So the key thing here is that this isn't you're not calculating the new weight, you're calculating your delta, the change in your weight. So what you do is you inherit your previous weight value, and then you just sort of modify it by whatever the new weight is here. So in this case, my delta in this for x1, my delta is -8. So I'm going to take my previous value, I'm going to add -8 to it, and I'm going to get a result. Here, my previous thing was 1, my delta is going to be 3, so the result is going to be 4. So does that make sense?
Yeah, I couldn't add. I kept looking at that -8 as the regular 8.
Mm-hmm. Okay, perfect. And then, so remember, and these values here, these are from this table here. So remember, you're given these values. You're saying, okay, I have in my data table, I have these values for X, and then the actual prediction associated with it. So when I have these values, my actual thing is here. These values, my actual thing is here. These values, my actual thing is here. So like, just like in our exam, where's our exam? Is it this? It's this table here. So this is exactly what you're looking at here. These are my actual X values, and this is my actual prediction. And then you're given, in addition to that, you're given your weights. So I think we said that, let me go to the previous page. Your weights are all going to be initially set to 1, and your learning rate is 0. So if I'm setting up the table, I'm going to use that table to do this. All my weights are going to be 1, and then my actual value here is here. And then remember, all you have to do is you plug in the, you multiply and then sum up the weighted sum of these features and get that. You use your step function to generate a prediction. You compare that to the actual value. So is everybody clear on how each column is generated for this table? And by the way, one thing that I will highly recommend with this, because one thing that I saw last quarter is like something like a perceptron is conceptually very simple, but it's the kind of thing where it's worth actually doing a practice problem. Like it's worth taking this example and literally working through it and just making sure like you're kind of familiar with it. Because what we ended up seeing last quarter was a lot of people just kind of made very basic errors in terms of what they include, what they didn't include. And it's just like any math course that you'll take, right? It's important you have to know the theory, but you also have to do the practice, because you got to make sure that this is sort of muscle memory for you. So I would highly recommend, like, it's not enough just to know what these steps are, but to actually just work through a problem and just make sure you actually kind of have the muscle memory for doing this. Okay, did I screw up here? It is quite possible I screwed up here. Okay, sum for row 2 is, so that's -7, that's 8, that's 5, and that is 2. So that is, did I do this wrong? That's 9, 11 minus 4. Oh, no, I think I got that right. Right, so this is, so, okay, so here, so I have my new, oh, maybe I got that. Maybe you're right. I think I got, no, I think you may have gotten it right. I think I had to multiply this term. Okay, I may have screwed this up. Okay, so wait, let me just see this. So this is gonna be -7. This is gonna be 8, 5, 8. So that's 16, 21 minus that. So that should be 14. Right? Am I getting that right? 8 plus 5. Oh, sorry. No. Mark, I think you're right. You don't multiply that. That's just a 2. That's not multiplied by anything. So -7, 8, 5, and 2. Yeah. So that should be 13, 15. Yes, that should be 8. Yes. So Mark, you're correct. Let me fix this in real time so I don't confuse anybody. So you're absolutely right. So that should be an 8. Thank you for catching that. Okay. Luckily, that doesn't change my prediction, so my slide isn't completely messed up. But okay, so but that obviously shows a good point there. Like it's important to try and keep track of that. But so once you've updated your weights, so now the new weights here are -7, 4, 5, and 2. You then take the next row, you do that weighted sum, which as you can see here, I kind of screwed up on, but it would be -7 plus 8 plus 5 plus 2. And if you add that all together, you should get 8. And so since it's greater than 1, you predict a 1, but look, my actual was 0. So now I have to adjust back the other way. And if you remember, here I'm doing, now it's going to be a negative. So I'm going to multiply whatever my X value was by a -1, and that's going to be my updated learning rate. So here, my X value was a 1. So now my update's going to be a -1. Here it's 2, so -2. Here it's 1, so -1. So I update that accordingly. Then I multiply that through. I'll get my weighted sum here, my prediction, my actual, and look at that. I'm done. That, well, regardless, all I would have to do is a single epoch. But that's generally speaking what you would do for a perceptron. So if we are looking at our problem space here. So this is, so if this is our sort of initial thing, is there any different? Why is this table written here? But yeah, so it would end up looking something like this, right? Where if you have your x1, x2, and y, and you have your associated initial set of weights, you just sort of recreate that table and you work through that there. So any questions in terms of how we generate, how we would sort of, if you're given a perceptron on the exam and asked to kind of iterate through it, how you would do that? Okay. Oh, question 4B. 4B, did we not? We skipped 4B. Uh-oh. 4B. Oh, you're right. We did. Okay. So yeah, thank you for flagging that. Okay. One strategy, reduce variance and improve generalization is regularization. Okay. Period below, blue lines are logistic regression with regularization. Black lines are logistic regression with, so which one, in which figure is L1 regularization used and why? Okay. So we're looking here. So we have, so our blue line is our original curve. And then in one of these, we've applied an L1 regularization to it, and the other one we haven't. And your question is to try and figure out which one is which. And I'm not particularly fond of this question because I think it does. There's a reason why I'm not fond of this, but yeah, okay, good. So it should be A, but let me ask you why it should be A. And the person who did this example actually created an error, and that was good. Okay. Yeah, so essentially what you're seeing here when you, by this line essentially flattening out, is you're essentially zeroing out this coefficient. You're saying the coefficient along this axis is essentially being zeroed out. Now, arguably, we should have made it a perfectly vertical or perfectly horizontal line to say that it's been purely zeroed out. Here, there's still a bit of a slide, but I guess you could say L1 doesn't always completely zero out coefficients. It can just reduce the magnitude of them. Whereas here, if anything, the coefficient associated with this x-axis is sort of to a greater degree. So if anything, there clearly is no regularization happening here, whereas here we're clearly approaching more of a regularization. So the whole idea here is if you're looking at sort of this is probably like a two-dimensional representation of a multi-dimensional thing. If this is my baseline here, there's obviously a coefficient associated with this feature. As I am regularizing either an L1 or an L2, I'm minimizing the magnitude of the coefficient. And ideally with an L1, I actually completely zero it out. So if I zero it out, then effectively this goes completely flat because there's no associated effect of this feature on the overall predictive model. So yeah, so that's 4B. So thank you for catching that because we definitely should have discussed that. Okay, so then 5B. So this was a question that said, we had this perceptron convergence theorem. It proved that the learning model will find a solution that will converge if a solution is possible. Based on how this data has performed, do you think it will converge? Why or why not? So what do you guys think? Will this data converge? You might look at this and say like, well, I haven't done anything. So why would I know either way? But you're not given a lot of detail, but there is one kind of useful bit of information here, which is that rows 1 and 3 have the exact same x-axis values, but you have different associated labels. So 2, -3, and 1, 2, -3, and 0. So if you have a data set where you have the exact same set of feature values, but producing different predictions, do you think the perceptron will ever converge in that case? Okay, perfect. Yep. Everybody in the chat's hitting it, right? Clearly not, it's not linearly separable. It'll get stuck in a loop because first it'll correct for this one and make it so that it'll predict a 1, then it'll hit this and say, oh, wait, I need to correct it to now predict 0. And so exactly right. It'll never actually converge based on this particular data. So, okay, so we are almost done. And in the interest of time, I'm going to go through this last question really quickly, but I will say here that this is one of those questions that is written in a way that just seems confusing, but is actually relatively simple. So I'll give you guys a second to read through this, and then we'll kind of talk through it. Okay, so there's a lot there. This is just kind of walking through the steps of it. And what we're really talking about here is this model here. So this is really what we want to focus on here. So we're saying we have 2 clusters and all the clusters are contained within this bubble here with a radius of 1. And that there is and then there is this sort of D value here that is sort of separating the 2 clusters from the y-axis. And then we say, okay, well, there is a sort of the mean value here of these clusters. And you'll see that it's not necessarily located at the geographic center because, you know, the values in this case could be clustered in this area. It's within this thing, but it's not uniformly distributed. So we have these means here. And then it gives us one more bit of information here where it says that, let's see. Okay. That minus, okay, there's a number of points. Okay, so then the important thing to note here is that this note here, it says that for all points within that cluster, the distance between that point and the mean is going to be less than D, that D value, less than this value here. And the question it says is, okay, so if you initialize the clusters at that mean, can you prove that that our method will converge after the first iteration? So i.e. first iteration means, if you remember from K-means, and we'll walk through a K-means example. I also have that in the slides, but we don't necessarily need that for this one because this is just purely for sort of a theoretical thing. So it's saying that for all of these points within C, they are closer to the mean than this D value here. So it says prove that this will converge within 1 iteration. And so the answer to this is you just need to talk about this from a logical perspective. And you say, well, if this is closer than D, then you know that when you apply them, you're always going to apply it to the right cluster, which means that it's not going to update. And so even though you may update the cluster value, although in this case, since it's already the mean, you wouldn't update it. Since already the cluster value, there's going to be no updating. And so it will have converged at the first iteration. And so then the next question says, if D is large enough, give a simple explanation for any initialization that will converge after the first iteration. And so here, again, you're just being asked a logic question. And here you'll say, okay, well, if D is large enough, if it's pushing these clusters far enough away from each other, it doesn't really matter where you initialize this. Like you can initialize your thing right here. And if D is large enough, it doesn't matter if you have a point right here, it's still going to be close enough to this cluster. And so again, it's just talking through the logic of it. It's kind of just a deceptively complicated problem with actually a really, really simple solution. The final thing for that, I'm sorry, I'm running through this a little bit fast just because I want to be mindful of the time. And I want to give you guys a little bit of a break and still go through the slides and all that jazz. But if you recall from our lecture yesterday, we had sort of talked about the fact that one of the downsides of K-means is that it's very sensitive to outliers. And it also doesn't handle data that's not really shaped particularly well with this. So figure load approximately. So, and then the question is like, okay, draw below what you would expect a K-means clustering to look like, and then what might be a better algorithm to handle this. And so I will just kind of just pop up here and show you what this would look like. But so generally speaking, right, because remember K-means will end up doing some kind of linear, also kind of have its own linear decision boundary because it's all about nearest neighbor. So you're going to get a centroid value. And then with everything is proximate to that, which will end up being sort of a linear plane, it'll do that. It'll end up doing that there. So you're going to get something that looks like this, which means as a result, you're going to get these weird things there that clearly should be part of this, but aren't. So, and then if you recall, we mentioned at the really the tail end of the last lecture, the notion of DB scan, which is this idea that it was density based. And remember, it was that cluster and outer model that sort of deliberately eliminates outline points. And so that's what like a DB scan looks like. And so we would say in this case, probably a DB scan would generate a better performance in terms of dealing with data that's clustered in this manner. So, okay, I know I ran through that question, but let me just kind of pause there. And well, firstly, so that's the exam in a nutshell, but let me pause there, see if you have any questions, and then I'm going to give you guys a really well-earned break and then get back to some slides. Okay, cool. Well, it's 1:23. Should we just make it like a 5-minute break? Come back at 1:28-ish. And then I'm just obviously hanging out here. So if you have any questions, you can keep asking. But yeah, let's come back. Let's do a 5-minute break. And then when we come back, I'll go through the slides. All I want to do is have some fun. And I'll pause the recording while we're doing this. Okay, I just wanted to mention that during the break, somebody quite correctly called me out that my math on this third cell was wrong. This third row was wrong. So I updated it, but yeah, and on the slides, it will be updated if you're accessing these later. But just be aware that when I first went through them, this math was wrong. And so if you're scratching your head being like, TA doesn't know how to do maths, you would be correct. Okay, so yeah. All right, so welcome back, everybody.
So just real quickly about that third row. Should I say
Oh yeah.
-1?
Sorry, which one should be -1?
The third row?
Yeah.
The sum?
This, oh, should it be -1?
Yeah.
Oh, did I do this completely and I still get it wrong? So this is -24.
Oh,
This is-
20. I forgot to multiply. Never mind.
Okay, cool. Okay, awesome. Okay, so I am bad, but I am not irredeemably bad. So, all right, let's go to the slides. Let me make sure I don't am I missing anything in the chat. Okay, cool. All right. All right. So, because I didn't get to meme you yesterday, I kind of have to go overboard with the memes today. But yeah, I felt like Savannah was my little distraction to try and prep for the fact that I didn't prep for the material yesterday. Although ironically, we got to end up with so much material that we went over, it seemed like. But yeah. And by the way, I'm sorry again, she was so loud yesterday. I hope that wasn't too distracting. But obviously, we shipped her off to a caregiver right now, so she will not be bothering us anymore. Yeah, just kind of a status check. Obviously, midterm is coming up this Thursday. That's kind of what we've been dealing with. Project 3, kind of nipping right on its heels, doing 10 days. So hopefully you guys have made progress on it. I do want to update you that I think we're prepared to cancel the Kaggle component of the competition. Orpaz has been unable to get that to work, and I haven't really had time to look at either, so I think we may just end up canceling the Kaggle thing. I will say that in general, Kaggle as a platform does not work particularly well. So that might just get ended up, but you'll receive guidance from ORPODs if we end up doing that. And then finally, homework 3 is due right on its tail in about 2 weeks. So just, do be aware of those deadlines. They are coming up.
Oh,
So-
quick question.
Yeah, absolutely.
So if we don't do Kaggle, will there be like, I don't know, some sort of I can't even think of a word, like a target, like accuracy or measure that you're gonna look from us then, or
We'll talk about it. It's a good question. For the moment, the answer is going to be no, because like we had talked about trying to score it ourselves and doing something like that, but in the end, it just proved to be too burdensome. So if we can't get Kaggle to work, I think the idea is we'll just like project 1 and 2, you'll be graded for completeness of the project and not necessarily on performance of your resulting models. But ORPOS will issue guidance on precisely how we're going to do that. But yeah, great question. So I wanted to, so for this thing, I wanted to talk a little bit about kind of helping you guys prep for it and the type of questions you might get asked and just kind of thinking through some of these things. So generally speaking, these are maybe some good things to, like, as you're going through, to check off and make sure you're comfortable doing these. The first thing is going to be learning a model. And that's precisely what we did with the Perceptron just now, right? You may be asked to learn a model where you're going to be given sort of basic parameters, and it's going to be your job to update the model accordingly. And realistically, when I was thinking through this, there's really only, I would say, 2 sort of models that I could expect realistically us to ask you to solve by hand. And that's Perceptrons and KMeans. And so Perceptrons, we already went through the example. And KMeans, I'll go through an example. I have another example in the slides as well. So I'll go through examples of both of those. The other thing you might be asked to do is just generate predictions. And that's, you literally are going to be given a set of inputs. You're going to be given a model, and you'll be asked to plug it in and solve for it. So naive Bayes, for instance, we did last week. We went through an example of that where we were given sort of a set of training data. We were given a set of values, and then we used that to generate a prediction. Neural net, there's an example of it in homework 3, but essentially you're just plugging it in, much like you do for the Perceptron. And it's just a little bit more complicated of a cascade, but you're literally just going through this entire process where you're just doing the weighted sum, you're outputting it, and eventually you're generating a prediction for it. So linear regression, SVM, again, those are just quadratic formulas. You would be asked to plug in and generate either a prediction or a class based on that. KNN, we did an example of these in the homework, but just use the nearest neighbor to generate a prediction. And yeah, I think those are realistically models that you might be given some data and asked to use to generate predictions on. Another thing that you will almost certainly be asked some form of question, I would usually assume, is some kind of either metrics generation or interpretation question. So you may either be given a set of raw data and asked to generate metrics associated with it. You may be given some results or performance and asked to interpret it. But yeah, generally speaking, just be kind of prepared to solve like that. So understanding the types of loss functions we look at. Generally speaking, being able to look at those basic statistics tables, like looking at your p-values, your r-squared t-values, what are those telling you? Classification metrics, so being able to calculate accuracy, precision, recall, and F1 score. I think those are very reasonable things to be expected to do on an exam, and we'll go through an example on that. Confusion matrices, so if you're given a confusion matrix, sort of being able to interpret it. And then ROC/AUC, this was actually another question I think you could potentially be asked for, is like, if you're given, could you either plot or interpret an ROC curve? I think that would be that would be a common question I think you could expect to have to address. Let's see. comparative assessment. Okay, so this might be sort of another thing. And this is what we talked about in general for all of these models. It's good. And when you're studying, I'd almost recommend putting together a table when you sort of for each model, like work through how does the model how does the model learn a model of the data? How does it apply a decision boundary? What data does it tend to work well on? What are its advantages? What are its drawbacks? And just kind of have that comparative assessment in your mind, because again, it's quite possible you might be asked how, and that was what you saw with the clustering thing, right? That last question said, hey, okay, K-means if it dealt with this data, how might it handle it? And what might be a better model to handle it? And so as you're working through your clustering approaches and your classification and your regression, just thinking through all of those things, how they learn the model of the data, how they generate the decision boundary. Generally speaking, what are the advantages? What are the disadvantages? What data does it tend to work well on? What does it not work well on? If you can kind of answer that for each of those models, I think you should be relatively well equipped to handle those types of questions. So yeah, and again, just I'll talk about this a little bit thing. So like I said, be prepared for be prepared to sort of have a conceptual understanding of how a particular model learns the model of the data, how a prediction is then applied, how is the decision boundary generated, how is it determined, again, strengths and weaknesses, and then also just kind of having a sense of whether or not, those particular models have tools to try and optimize performance, things like the bias and variance trade-off. Like, do models we had talked about, does obviously like a perceptron clearly does not have an explicit optimization step to it. Other models do, and just kind of thinking through all of that and just kind of having that ready to go. I should add some clustering things here too. But again, for your data processing tools, understanding the sort of the choices that come with data imputation, how you handle categorical encoding, how and whether or not to scale your data, dimensionality reduction. There's the whole question we've had around data splitting, doing things like a stratified shuffle split, cross-validating. I know there's been some really active conversations in office hours, but again, just kind of being generally aware of those options and some of the choices and the trade-offs with them. Then we talk about parameter optimization. So things like, loss functions, your optimization functions like gradient descent, and your normalization techniques. And just kind of understanding, generally speaking, how they work, what some of the trade-offs are. And again, your models. So for regression, we've really covered linear and KNN. For logistics, we've done logistic, SVN, Bayesian, KNN, decision trees, random forest, generally ensemble methods, perceptrons, neural nets, K-means, and then I guess just be aware of some of the other ones like dbScan that we talked about in lecture on Thursday. Yeah, I think, yeah, if you do all that, you should be well equipped for the exam on Thursday. But any questions beyond that in terms of scope? Okay, cool. So getting into model solving. So I put up examples of both K-means and Perceptron. We went through the Perceptron one already, sort of, so I'll just do the K-means one. But if you recall from yesterday, so being mindful of the time, I'm not going to kind of go into this in detail, but sort of K-means was the idea of this clustering thing. You sort of define an arbitrary start to a cluster, K number of clusters, and then you assign sort of every value to that point that's closest to it. And once you've gone through and you've iterated your entire data set and assigned it to a cluster, you then recalculate the center of that resulting cluster. And that's your new centroid. And then you go through your data again and you see if with this new centroid, all the values are still the same or if they've shifted. If they shift, you then recalculate. you keep going until you've converged on a stable kind of division of your data. So let's look at sort of a real example of this. So in this corner, we have 7 data points with associated X and Y values. And for this example, we're going to start putting our centroids at opposite extremes of it. So our centroid values are going to be at 1, 1 and 5, 7. And then we're going to go through each of our data point and we're going to assign them to a cluster based on whatever is nearest. So this is cluster 1. This is going to be cluster 2. So as we go through it, obviously ID 1 at 1, 1 is going to be the closest. 2, same deal. 3 is an interesting one because it's literally midway in between those. If you calculate them, it's equidistant between the 2 centroids. So here we're going to have to apply a tiebreaker. And so for this one, I'm going to apply it to cluster 1. But just so you're aware, in that case, we'd have to do a tiebreaker. Then 4, 5, 6, 7, those are all relatively closer to the second one. So we apply it to that one. Now that we have these sort of initial things for our first epoch, we then recalculate our centroids. And again, to recalculate, you just simply take the mean value of each of these. And so for this one, you would literally take 1, 1.5, and 3, divide by 3. That'll get you 1.83. You get 1, 2, and 4, divide that, and you get 2.33. That's your new centroid. And then same thing with this one. You just take the mean of these four, and you get the new value there. Then you run through it again. And now what's happened was, even though these are equidistant, 3 is now much closer to the second centroid. So now we push 3 over here, and then we adjust our centroids accordingly. So now there's only 2 values in this one. So now we take the new mean of that, which is 1.25 and 1.5. And now we take the updated mean of this one, which is now 3.9 and 5.1. And then if we run the model again, we're going to see that now we've established a stable clustering of our data. Points 1 and 2 are going to remain with this centroid. Points 3, 4, 5, 6, 7 will remain with this centroid. There won't be any updating of it further. So yeah, very simple, very easy kind of way to sort of run a K-means. So do I have any? Yeah, so that's K-means in a nutshell. So if you're given this data table, if you're given the number of Ks and your initial starting values, you can kind of just run through it like this and ideally converge relatively easily. So, okay, so good question. So there's a question in the chat about if we can use calculators. That's a question for Majid. I don't have any guidance on the specifics of the test proctoring yet. I think if you're not allowed to use a calculator, we would try to make the arithmetic relatively simple and easy so that it wouldn't be something that would hopefully trip you up. Like I know something like this, you can potentially, it's simple, but it can also be relatively tricky because you can get, just doing your distance formula across 2D can become difficult. So it would probably be the example if we do something like this where it's either just like blatantly obvious that the relative distances of these things, like you don't actually have to do the math because you can just eyeball and be like, oh, okay, this is obviously associated with it, or the numbers would just be so easy that you could kind of calculate it. But yeah, we would, if you're not allowed to use calculators, we would adjust for that. So again, here's the Perceptron notes. We sort of went through that in the interest of time. I'm not going to kind of reiterate that, but those notes are there. We'd sort of run through that. Metrics, again, just so there's kind of a quick sort of thing about that. If you're given a confusion matrix here, and you are asked to sort of calculate accuracy, precision, recall, and F1 score, could you guys do it? Hopefully the answer is most of you, and hopefully the answer by next Thursday is all of you. But just in case, I kind of wrote out the solutions. One thing that I will note, just to be careful about, is be careful about your axes values, because what is a positive versus a negative? Like in this case, your true positives are 100, not 50. That's your true negative. So just one thing to be mindful of. It's not always a positive, negative, positive, negative. It could be in this case like a negative positive. So just watch out for that when you're calculating your own values. Because obviously, if you try to do something like precision or recall, which is really, really depends on your positives, you don't want to end up accidentally calculating the inverse of that, which is your negatives. So just kind of be aware of your column and row values. But again, accuracy is just the overall number you get right. Your true positives and true negatives divided by everything. Your recall it's essentially saying how many actual positives do I get? So it's the number that I predict versus the total number of actuals that are out there. Precision is basically just saying like every time I predict something, how often do I get it right? So there it's like looking at my predicted thing. So it's, out of every time I predict, how many do I get it right? And then F1 is that the harmonic mean of precision and recall. So it just kind of balances those two, but with an eye towards sort of class imbalances and very sort of focused on that. Let's see. So yeah, that was kind of it that I had in terms of prepping for the exam. Obviously, Tuesday is going to be a review. Office hours, I think next week will be pretty heavily focused on prep for the exam. But yeah, you guys, you'll do good on this. I don't think Majid's going to kind of be too sadistic in terms of this exam, and you've been following the material, so you guys are going to be great. But any questions on this before we break? Okay, well then have a great week, everybody.